Chapter 6, Understanding Organic Reactions, is really the last of our background chapters, or sort of like toolkit chapters of items that are going to help you throughout all of organic chemistry. After this, we're going to start getting into specific reactions and mechanisms, starting in Chapter 7. So to begin with, let's talk a little bit about how we draw equations and what different things mean in equations. So on the left-hand side, normally we call these reactants. Sometimes organic chemists will call some of them SM, or starting material. We'll draw an arrow, and an arrow just means that there's some kind of a transformation that happens, some kind of a chemical reaction. And we can put things above and below the arrow, and we can number things that we're going to react with. So a lot of times, instead of putting all of the reactants to the left of the arrow, organic chemists will a lot of times pick the primary organic chemical and put that to the left of the arrow, and that's what I would call the starting material or reactant. And then the things that would go here are considered reagents, or the things that are trying to make a reaction happen. Now, above and below the arrow have no meaning, but if they're numbers, the numbers mean sequential order. So it doesn't matter if you put it 1, 2, both below the arrow, 1 above, 1 below, 1, 2, both above the arrow, those all mean the same thing. There's some other things that sometimes we'll put in besides reagents here. Sometimes we'll put in H nu, which is light energy. It's the energy of a photon of light. And that means that the reaction is catalyzed by light, or light somehow encourages the reaction to happen. Sometimes they'll put a delta, which just means heat. And often the solvent is included, but sometimes the solvent is not even included. So typically, if the solvent is important, it'll be included. If it's not important, sometimes it's not even included in the equation. And then at the far end is always going to be your product, or products, depending on the reaction, if there's one or more product. Now, there are lots of different kinds of arrows in organic chemistry. And so you've probably seen this one before. That arrow shows that the reaction is reversible, and it's considered an equilibrium arrow. If the reaction goes nearly all the way to completion, we don't usually write that, and we'll just write an arrow to the right. So that's just a reaction arrow. If we write an arrow with heads on both sides, that's a resonance arrow. So that's different from the equilibrium. That's what signifies that resonance is happening. And if we do a curved arrow, that's a mechanism arrow, or electron movement. So those are some of the most common arrows that you're going to see in organic chemistry. In section 6.2, we'll look at kinds of organic reactions. There's actually an additional reaction that's not in the book that I like to add. So let's look at the different broad types of organic reactions that can happen. So the first type is going to be a substitution reaction. In a substitution, we have some kind of a carbon bonded to a group, we'll call it CZ. We'll react that with some new group, Y, and the Z will be replaced. So we get CY plus Z. So the Y substitutes for Z in the product. So during this reaction, we've got one sigma bond breaks. That's the CZ bond. And one sigma bond forms. That's the new one, CY. So whether or not this reaction occurs really has to do with which one, Y or Z, is happier on its own or is more stable on its own. So in the end, it's going to come back to pKa's. The second type of reaction is an elimination reaction. An elimination reaction, we've got carbons with an X and a Y on adjacent carbons. And what happens is the X and Y are eliminated from the original molecule, and they leave. So in this reaction, we're going to break two sigma bonds, So 2 sigma bonds break, CX and CY. Then 1 pi bond forms between the 2 carbons. And then depending on the molecules, you could say an XY bond forms. That's not as common. But in the starting material, we lose 2 sigma bonds and we form 1 pi bond. The third reaction type is an addition reaction. In an addition reaction, you have a carbon-carbon double bond, so you've got a pi bond. And we're going to add XY to that. And what we end up with is a new molecule with X on one carbon and Y on the other. So in this one, we break a pi bond, and we form 2 sigma bonds. And this is really the opposite of the elimination reaction. If you look at it, it's just like as if you did the elimination reaction backwards. In the elimination reaction, you have CXY, you lose XY, and you get a carbon-carbon double bond. And the fourth one, the one that's not in the textbook, is a rearrangement. In a rearrangement, you don't add or take away anything, your molecule just changes. So an example of a rearrangement would be if I have butene with an acid catalyst, it rearranges to 2-butene. The proton adds at one point, but then it comes off at the end, and so there are no additional atoms on the product molecule, and there's nothing lost. All that happens is that the atoms are there rearranged. And if you want to see what rearranged, here we have 2 hydrogens at the terminal carbon, where here we're going to have 3 hydrogens at the terminal carbon. The other difference is here we have 2 hydrogens at this carbon, while here at the end we only have 1. So in the end, effectively what happened is one of these hydrogens moved over. That's not the mechanism, but that's effectively what happened.